Hello everyone, welcome to my channel. Today in STAAD we're gonna learn how to define irregular grids, inclined supports, displacement of the supports like modeling settlements, variation of temperature, impose strains like elongation and shrinkage. And to do so I'm gonna use this example here. It doesn't look like something that you will use in the real world, but it's gonna be useful to show you everything that I want to. So let's begin. So as always, I'm gonna start from the very beginning. So we're gonna create a plane model. We're gonna call it sample 2. I'm gonna leave the length units in meters and the force units in kilonewtons. As we're gonna work in a plane, I'm gonna just by default leave the add beam option highlighted. So we have this grid, the by default one, and we're gonna start defining the irregular grid, because as you have seen on the model that we want to build, we have irregular spacings. So we go to create, we're gonna define here an irregular grid, and in the relative grid-like distances in X, if you go back to the image that I showed before, you will see that there is a space of, well, the grid is like 3 and 4 meters in the X direction and 3 and 5 in the Y direction. How the irregular grid works, it works with a relative distances. So this 4 is going to be measured from the previous grid line of this 3 separation. Oh, we have to put it a name, so it will be grid 2. So as you can see here, nothing has changed because you have to activate that grid line. So now we have our irregular grid. This is 3 meters and this is 5 meters. And in this direction is 3 and 4. So we're gonna define the structure just by clicking on the nodes here and here, 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 and here. Done. After we have defined the beams, or the lines that are gonna define our beams afterwards, we go to click, close, and perfect. We have already defined everything. I'm gonna change the point of view to show just the frontal view, so it will make it easier to understand what I'm doing. So I'm gonna start defining the cross sections. I'm gonna use an IPE 200 for this, and these bars, and I'm gonna use a rebar here to show like if it was something that is holding the rest of the structure. Okay, so I'm gonna go to properties, section database. I'm gonna go to Spanish code, IPE 200. I'm gonna add it. And for the rebar, I'm gonna define it as a circle of 0.04 because it's a 40 millimeters bar. And I'm gonna assign those cross sections. So the IP 200 is gonna go to here, 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 and the bar is gonna go to here. We close this, we check if everything's okay, we go to the render view, and You can see here there is the IPE and the bar that is like holding this part of the structure. So that was easy. Now we're gonna I'm gonna define the supports. We're gonna create a fixed support for these nodes. I'm gonna put the numbers on the nodes. If you wanna see the numbers of the nodes, you have to go here, node numbers, apply, or okay, doesn't matter. And there you go, you have the numbers of the nodes. It's gonna make everything a lot easier. So I want to assign a fixed support here, and node number 1, node number 5. So I created the support already, and use cursor to assign here, and assign here. Now we're gonna start with one of our subjects of today. That's gonna be inclined supports. So what I want to do is to, okay, fine. I want to define a support that is inclined following this direction. Okay, following the model that I showed you before. So to do so, and it's a pin support, it's not gonna be a fixed. So I have to go to create, incline, and now you have here like two main different ways to define the inclined support. You can define what is gonna be the direction of the support by defining a STAAD reference point. So this is gonna be your inclined support, and the inclination is gonna be this one. I want this to be the X direction. So what I can do is to define by coordinates a point here that can be the coordinates of point 3, or in fact I can just use point 3 as a reference. So if I would like to define the coordinates, I have to put them here. But if I'm lucky enough and I have a point of reference, so I can use this reference join number 3. The support is going to be pin. Click on add. So now if I click here and assign cursor, we use cursor to assign in node 4, what it's going to do is to define the x-axis of this node, of this support, to point to node number 3. If I use this support already created in node number 5, it will do the same. It will incline the support by pointing to node number 3. So as I wanted in node number 4, that's it. Check that it doesn't appear anything that is telling you that is pointing to node number 3. It just appears this box like showing that the reference to the support. So if you wanna check how this support is defined, you have to go to edit and check the properties of the node. So that was one important thing. Now what we're gonna do is to define a settlement or a displacement of node 1 of 1 centimeter. So we're going to load. We're gonna create a new load cases. We're gonna leave this title by default because we don't really care too much about this now. Once we created the load case, we're going to go to add. We're gonna go to what is it? Node load support displacement. So here we define what will be the node displacement. It's gonna be settlement. It's gonna be a minus 0.01 meters in the direction Y. So let's add it, and once we have it here, we have to assign it to the node that we want. So we're gonna go to assign to this node. It's assigned. Now that node has suffered a settlement in the y direction of 1 centimeter. We're gonna keep following the model that we want to create. The model had an X load, point load in the middle of this beam. So we're gonna add in member load concentrated force. It was 40 kilonewtons, pointed in the X direction, general X. I'm gonna work in the general with the general axis. You can define the force in the local axis of the beam, and therefore will be Y local, but I prefer to work with a global axis if I can. So add, and we're gonna assign, whoop, I missed something. I have to define the distance from one of the edges of the beam where the load is gonna be applied. So it was in the middle of the beam, so it's gonna be at 1.5 meters from D1. You can define if the load is gonna be, it has an eccentricity, and that will be D2, but as I'm gonna apply the load just in the center of the beam, so I'm just gonna define D1. Yes, I'm gonna wanna save. I'm gonna change this. I'm gonna assign here. Okay, that's what we wanted to. Now the model had a moment applied here, node number 3. So we're gonna add it to. We go to nodal load. It's gonna be a moment. It's gonna be a moment in the Z direction, positive, because it goes from X to Y. So it's positive, perpendicular to your screen, to point to your face. So let's add that moment, and we're gonna assign it to node number 3. Again, assign. There it is. If you wanna see the load values, you have to go here and show load values, apply, okay. The MC should appear here soon. I don't know why it hasn't done yet, but it will do. Now we have a vertical, a UDL, uniform distributed load in this beam. If you want to see the beam numbers, so you just have to go to the screen here, beam numbers, apply, that's it. So we have a UDL applied in beam 5. So we're gonna add it, member load, uniform force of what was 20 kilonewtons per meter, and pointed minus 20 kilonewtons per meter, pointed down because the y-axis is pointing up. So let's add it, use cursor to assign, that's it. Why is it not showing the moment? I'm gonna do something just to okay, and now is it shown? No, I don't know why it wasn't showing before. The moment, as you can see, is 50 kilonewtons per meter, and minus 20 kilonewtons per meter here. Now what we're going to do is to introduce the variation of temperature in bar number 4. It's going to be an increase of the temperature of 30 degrees. So we go to load case, add, we go to what it is, temperature loads, temperature change for axial elongation, so it's going to be 30 degrees. Let's add it, close, and we're going to assign this variation of temperature in beam number 4. Those arrows show that we have applied the variation in temperature. What we're going to do now is to define the strain. There's going to be a strain gauge of 2 centimeters on beam number 3. So we go back to load case, add, you have to define that in temperature loads, strain, and as it's going to be a strain gauge of 2 centimeters, we go to minus 0.02, add, close, and we assign it to beam number 3. Perfect. So more or less everything is done. I'm gonna close this. What I'm gonna do now is to define that we want to perform our analysis. So as we don't have anything moving, we don't want to know the mode shapes or anything else, just click on load data. That will do the job. And run. Yes, I want to save it. 0 errors, 0 warnings. Everything's perfect. That's what we want. So let's click on done. Okay, and check the results. So what we have to do now, well, everything has worked. So those are the stresses on the different beams. As always, we want to we have to check if the results that we have gotten from STAAD are reasonable. So how? First, we're going to check the reactions. We go to Node, Reactions. Oh, yes, something else I'm going to teach you. When you click on Reactions, you get those boxes here showing you the values of the reactions in the different directions. So you want to move those boxes, you have to go to select text cursor and move them. They're kind of annoying sometimes, so keep that in mind that you can move them. So as we were expecting, we have a load here of 40 kilonewtons. So we should expect a reaction in the opposite direction of more or less 40 kilonewtons, because okay, this support here is going to develop some reaction according to this load, but it's not gonna be too much, because this load is really applied really close to the support. So this support should develop more or less reaction. So there you go, we have 36 kilonewtons in the opposite direction. So that's working. How to check now is, for example, we have here an axial force Fx of 6 kilonewtons, vertical force. So that 6 kilonewtons should be transformed in beam number 2 as an shear force, and here it is in part number 2, that axial force has changed to the shear force, and of course the shear force of beam number 1 should be an axial force in beam number 2. As you can see, you have the reaction 36 where the load is applied. That reaction, well, is almost disappeared. So you have just only 4 kilonewtons of shear force, and that's the axial force of beam number 2. Here in beam number 5, we should have applied a moment. That's what happened. So we have this moment has been distributed among this and this beam. So you have here the values, more or less. What we want to check now is if the variation of temperature has been applied well. So the variation of temperature of this bar, as this node is fixed and this node is pinned, so STAAD is telling us that the axial force by this variation of temperature has been 210 kilonewtons, and we should check that. So we're going to check that with this formula here. We have the model of elasticity, the alpha value, and the variation of temperature. So this is the tension that this variation of temperature has produced into the bar, as we have this area of the IP200. So if we apply the formula, so we get that we should be getting theoretically a force of 215 kilonewtons, and STAAD is giving us 210. Perfect. Also, we should check what is this, what has happened with the shrinkage of this bar of 2 centimeters. STAAD is giving us 50 kilonewtons. That's shrinkage, well, and with the composition of loads that are applied to the structure is 50 kilonewtons, 51. So if we go to the hand calculations, and well, here we have the area of the cross section of the bar, and here the model of elasticity of the concrete, because I made that mistake at the beginning defining the bar instead of being a steel one, being a concrete one. The length of the bar and the shrinkage applied, that would produce a force theoretically of 84.7 kilonewtons. And why is this happening? Well, this happens because this formula, the Hooke formula, depends, or it works, it will work properly or perfectly. It will give us like a really the same result if both ends of this beam will be fixed. But as this, bye motorcycle, thank you very much for your noise, sorry for this. As this end here is pinned, but this end is not free because it's a fixed node, but it's not a fixed end. I don't know how to explain that, but if we go to the animation, if we go to the section displacement, you'll see what I mean. So let me vary something. As you can see, well, this is moving a lot. Okay, so the shrinkage of this bar is not producing a really big axial load because it's quite flexible, the structure. So the results from STAAD are what they should be. So don't get scared because of that. Just check again, as I said in my previous video, check what you're modeling is what you want to model, and if it's the results are logical or not. And I'm gonna finish here. I hope you have learned a lot today. This has been a short video, but there were many things in it. Thank you very much for watching. See you next time. Bye.